Today, we want to continue looking at continuity. Remember that a function is continuous at a point if and only if the function is defined at that point, the limit as x approaches that point of the function exists, and those two values are the same. The function is defined to be the value of its limits. We can calculate the limit just by plugging in the point. So here we have the graph of a very strange looking function that's made to exploit these three things. And we want to decide where the function is discontinuous and why the function is discontinuous at each of those points. So, where's the function discontinuous? A, where else? B, C, D, is it discontinuous at E? No, it's continuous at E. It's pointy and it's weird, but that's continuous. So it's discontinuous A, B, C, and D. So now we want to make sure that we understand why it's discontinuous there. More than just saying there's a gap. We have to explain what kind of gap we're looking at. That's what discontinuous means. There's some kind of gap. What kind of gap are we looking at? So, F is discontinuous at x equals A, B, C, and D. Why is F discontinuous at A? It's undefined. There's an open circle at A, and there's no closed circle somewhere else. So F of A is undefined. Does the limit as x approaches A exist? Yeah, both sides of the function are headed to the same place. So the limit does exist, but there's no value of the function for that to equal. So note that the limit as x approaches A exists, but that doesn't help us. So note, limit as x approaches A of f of x exists. But that doesn't matter. The function is not defined, so it can't be the value of the limit. So A, discontinuous. What about at B? Why is the function discontinuous at B? F is undefined. Same reason. F of B is not defined. So F of B is undefined. That's enough to declare discontinuous. Does the limit exist? No, the limit doesn't exist. We're not approaching any particular value. From the left, it's headed off towards infinity. From the right, it's headed down towards negative infinity. Neither of those is an actual value. We're not getting closer to anything. So, and we wouldn't need to state both. Discontinuous if any one of the three things is not true. So we only need one, but not only is the function undefined, but the limit also does not exist. Part C, at C, f of x is discontinuous at C. Sentences are difficult today. I'm not sure why. Why is f discontinuous at C? Is the function defined at C? Yes, there's that filled in circle in that upper branch of the graph. So f of C is defined, but why is the function discontinuous at C? No limit. The limit doesn't exist. F of C, oops. The limit as x approaches C of f of x does not exist. We could note that the function is defined, But that doesn't matter because the limit does not exist. So we do have a value for f of c, but it doesn't matter because the limit doesn't exist. Also note that we have a left limit and a right limit, but since those limits are not the same, the limit doesn't exist. So the limit as x approaches c from the left of f of x and the limit as x approaches c from the right of f of x on f of x both exist, but they're not equal. So we are not approaching any one value. So that's why the limit doesn't exist, because the left and right limits are not the same. At D, what's going on? The two values are not equal. The function is defined and the limit exists, but they aren't the same value. So for part D, the limit as x approaches d of f of x is not the same as the function at d. The limit exists and the function is defined, but they aren't the same value. Discontinuous. The limit exists and the function is defined, but those two are not the same value. Therefore, the function is discontinuous at d. The function is continuous everywhere else. We say that a function is continuous on an interval if it is continuous at every point in that interval. Questions? Continuity is a pretty straightforward concept, but we needed to have some kind of definition for what we mean by continuous that's more rigorous than just can draw without lifting up pen. Especially of all the troll answers that would spawn. Well, why don't we just use a pencil? Oh, look, I'll just mark the spot that it's missing with a circle, and then I never had to lift up my pencil. And it's like, dude, you know what I meant? You're just being a jerk. It's like, I'm just asking questions. You're not just asking questions when you know the answer to the questions. You're just kind of trying to be a kid. You know what I mean? Anyway. All beside the point. We have to understand the concept of continuity, just like we had to define the concept of continuity. And the same thing happened with limits. We had this idea about one value approaching another value, but we had to define what we meant by a limit. We had this intuitive idea, but then we had to come up with a description for it. Just like everything in math. We get this intuitive idea. We see this one bunch of things, and then we see there's more things over here. We had to come up with some way to describe more things. We count them. There's 5 here, and then there's 7 here. So there are more, right? We had to come up with this intuitive idea of what More is, but we had to come up with a way of describing it. We had an idea about a limit. We had to come up with a definition for it that we can work with. We had a notion of continuity. We had to come up with a definition for what we meant. This is one of the reasons I like math so much. The words mean things. The symbols that we write mean things. Natural language doesn't do that. It like changes. Math, we've just been adding to it for thousands of years, just been adding more stuff onto it. There's another level to continuity, just drawing stuff. There's another level to continuity, and that's called differentiability. This is continuity plus. This is a stronger version of continuity. Differentiability is a stronger version of continuity. It takes continuity and adds stuff to it. What we want out of differentiability is for a curve to be smooth. The idea is we say a function is differentiable at a point if we can put a tangent line there. That's going to be our intuitive idea about differentiability. A function is differentiable let's use an alternate color to express. This is our idea. A function is differentiable at a point a function is differentiable at a point if we can draw exactly one tangent at that point. This means that a function will have to be continuous at the point to be differentiable. A differentiable function, if a function is differentiable at a point, then it must start off by being continuous at that point. So differentiability is a stronger condition than continuity. To be considered for the differentiable club, you must first be a member of the continuous club. To be differentiable at a point, a function must first be continuous at that point. In the previous problem, we can't put a tangent line at A because there's no A to put the tangent line. There's no point to attach the tangent line. Can't be differentiable if it's not continuous. If it's discontinuous because the limit doesn't exist. Like we had at x equals c. We can't attach just one tangent line here. The tangent line is supposed to skim across the curve. So we could have like a one-sided tangent here, but what about that? Or that? Also, what about down here? We can't even attach anything down here. I had to freeze time because when I first wrote this down, it fell off. And so that's why it's down here now. That one fell off. And if I try to balance a tangent line at that one piece, it starts swinging and flopping around. So there's too many tangent lines. There's not one slope up there. We could change what we need in this case by saying, well, what's the slope going if we just kind of follow from the right? It could be like some kind of like right differentiable. The new thing that we want to watch out for differentiable is like we had at point E on the previous problem. So the new thing is corners. Like we saw in the previous example, we have a function that's continuous. Our function is continuous at E, but it's not differentiable at E. Which slope do we use? The slope going into the point? Or the slope coming out of the point? If I try to put a tangent line at that corner because it's a sharp corner, it just kind of like teeters around. Teeters just like, so I'm like, oh, well, what about this? This is tangent to the curve at that point. And then it's like, it could fall over. So too many tangent lines we could use here. Oops, I smeared one of them. Too many tangents, not differentiable. We have to define what we mean by this differentiability, this ability to write one tangent line. Fortunately, we have the concept of continuity, and we also have the concept of limits. We combine those two things with what we want to do, which is find the slope of the line tangent to a curve at a point. And then we get a definition for differentiability. It was hard times back in the early days of calculus, because Newton would be like, oh, I can just draw it without picking my pen up. And it was like, oh, okay. And then you just put the tangents. You know, like, oh, can you always do that? It's like, oh, well, if you can't, then it'll just be like one little point that you can't do that, and that'll be obvious, right? And it was like, oh, yeah, okay. Then dude named Weierstrass comes along and says, hey, Newton, I've built a function that you might have a problem with. And he shows him a function that is continuous everywhere, but differentiable nowhere. It's like you can't. It's always continuous, but it's never differentiable. And Newton's like, oh, well, fuck you, man. And so then we had to become more rigorous. Like I was there. We had to become more rigorous about this. We had to define stuff. We had to start inventing stuff like limits and defining what we mean by continuous and differentiating this differentiability thing. So here's how we define differentiability. Once again, like continuity, this is a definition at a point. So a function f is differentiable at a point if and only if this is one way we can write this definition. I like opening up with this in our definition of differentiability, because what we're trying to do is find the slope of a line tangent to a curve at a point, which is just change in y divided by change in x. And this is how we say you can do that. Another way to say this is to phrase it the way we were thinking about it. Build a secant line that's a little bit far off. So C is the point we care about. Go a little bit away from C. Go a little bit away from C. And so we phrase it this way. We say the limit as h approaches 0 of f of C plus h minus f of C over h. So start off at f of C and then go a little bit away. The reason that we don't see the difference in the bottom is that, any x or c in the denominators, because they cancel out. Here's change in y is f of c plus h minus f of c. The denominator is c plus h minus c. So the c's cancel out and just leave the h. So this denominator we approximated our tangent line with a secant line by choosing a point nearby. H is how close that point is. What we want to see in this definition, is the slope. We're able to calculate a slope. Where this definition fails, at our new thing, where like a corner, is that as we're approaching E from the left, It looks like we have a slope of +1. But from the right, it looks like we have a slope of +2. The limit is not approaching the same value from both sides. The limit's headed towards 1 in this direction and then towards -1 from the other direction. So the limit is not approaching the same value. So we're using the same concept with the limit where everything has to be headed to the same point. So this is the idea behind differentiability. Questions? Our goal now is to find all the shortcuts to calculating the derivative at a point without having to use the definition of the derivative. Because the point of math, every math class, is to try to skip all the math and get to the answer, despite the fact that getting to the answer is never really the point of the class. Very strange. This is why people don't like math. As math teacher be like, oh, you've got to get the right answer. And then when you get the right answer, it's like, oh yeah, but you didn't support it correctly. But you said get the right answer, right? It's like, well, yeah, but getting the right answer is not important. It's like, well, then how come you're judging me based on the answer? The truth of the matter is, it's easy. It makes it easy for me to spot. That's why I give problems that have definite answers. So I'm like, oh, you're supposed to do a bunch of stuff and then come out with this number. The first thing I do is look at that number. I'm like, oh, okay, things must have gone well. Something went right. Then I go back and look at your work. Your work goes forward, but I read it backwards. And having an answer accurate to 5 decimal places tells me that things are going right. So I can kind of go through your work a little faster. That make sense? But ultimately, the point is to skip all the work and not write down all the steps. Okay, so this is our next big idea, is differentiability. I want us to think about what we're trying to do with this differentiability. We're trying to find the slope of the line tangent to a curve at a point. A function is differentiable at a point if we can do that. I also want you to think of, so I want you to see the slope formula. I want you to see the slope formula, us trying to calculate this slope when we're deciding if something is differentiable or not. I want you to think of differentiability as a stronger form of continuity. If a function is differentiable, then it is continuous, but a function can be continuous without being differentiable. And we want all this to reinforce the notion of a limit, where we're approaching a value. And if there's 2 sides, we're approaching the same value. Those are the ideas that we want to carry forward. We haven't done a lot of calculations with this because we're trying to build ideas. This week is about building ideas and then doing homework from chapter 1 and reminding ourselves of the stuff that we already know, or at least that we're pretending that we already know. Except for homework 1.6, which seems to be broken. So if you keep getting stuck on 1.6, I don't know why it's broken. But that one assignment, 1.6, is broken. So I just may go in and give you all points for it and hope that you all know about polynomials and rational functions. So we might just pretend on that. Any questions? Comments? Yeah. Okay, so think about differentiability, think about continuity, think about limits, think about the definitions and how unimportant the definitions of these things are when compared to the idea, the intuition behind it. We've got intuition and we've got our definitions that make our intuition rigorous. How's everybody okay? Everybody looks all sad. Is it because Friday's finally here, now it's all overcast? Why was it sunny on like Wednesday? Why couldn't it be foggy on Wednesday when I had shit to do? And now that it's the weekend, it's gonna be, why couldn't it be sunny now? I don't know. I'm not really, I kind of prefer it to be overcast. I mean, that's why I picked Skyline and not CSM or Pinata. It's all too sunny down there. Whenever there's like an opening day meeting in the district and it's at Pinata, I'm like, oh, great, I'm gonna burst into flames with Pinata. Any questions, comments, snide remarks? New assignments are going to be showing up from 1.7, 1.8, and 1.9. That's about this limits and continuity. And then next week, we're going to start getting more into chapter 2. All right, that's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Everybody have a good weekend. And thanks for playing.